Today's the 9th. We're almost halfway through February. It's crazy. Oopsie, that pen alert. Here we go. So we're going to start today talking about systems of linear equations. Oh, bless you. There are multiple ways to solve systems of equations. And before I even talk to you about what a system is, let me just walk you through a quick list so that we can kind of over the next couple of weeks check them off. It feels good to like say, okay, check, we know how to do this one. Check, we know how to do this one. Because in this class, my job is to attack systems four ways with you. Number one, the one we're going to do today, we're going to solve systems by graphing. And you'll find this lesson to be so simple, like just an absolute breeze. No issues here at all. The second and the third methods are what we call the algebraic methods. And they are in order substitution and elimination. The fourth thing is applications. And that's going to be where I think that was kind of why I decided to do this first was when you look at the Y-top, I actually saw one question on the Y-top that was um there were just two equations and it said like solve the system by graphing. And I was like, whoa, that was like totally weird that they would just ask a math question without like 50 extra words in it. So, but most system problems that you see are going to involve a bunch of words and they're situational, super useful mathematics, like super useful in a lot of different contexts. And so we want to be really good at this. But this allows you to solve a whole bunch of the Y-top practice problems that I wanted to do with you. I kind of was a little bit gun shy just because I knew that the skill at the end of it, like I could get you to write the equations. That wouldn't have been super hard. But using like elimination or substitution, that's kind of a thing. And so I can't just act like this isn't a thing. We have to spend time just learning the process of how to do systems, how to solve them, before we can get to step four, which is applying the methods to word problems. Okay. Like Marcia buys four Boogles and five Googles and spends $36. Steve buys seven Boogles and three Googles and spent $52. How much does a Boogle and a Google cost?
Are you saying
Questions like that are where systems are essential. Like essential, unless you have an extra couple hours sitting around to just guess and check. That's not what we want. So today is the warm up for this. It's like the precursor to all of this. I always get this one out of the way first because it's quite honestly the one that we would use in practical circumstances that we would use it the least. And it's just graphing lines. So having said that, we're going to do those four steps over the next couple of weeks: graphing, then substitution, then elimination, and then applications. But let's take a look at what it means to solve a system of equations by graphing. So when you think about linear equations, the root word of linear is line. And so what separates things like linear equations from things like what we talked about, exponential functions, quadratic functions, things like that, is that linear equations form straight lines. And so a system of two lines can look three different ways. Number one, you can have a pair of lines like this. And how many times do those lines cross each other? Once. So finding this point is going to be our focus. That point where the two lines cross is called the solution. Can anyone think of two? One of them's more obvious and one of them's a bit odd, actually. Can anyone think of two other things that could happen if I graphed two lines on the same piece of graph paper? They could. Thank you for saying that. That's exactly right. So another possibility is that I graph a pair of lines only to realize that they're never going to cross each other. And so when we look for a solution in a system like this, there isn't one. right? You could look as long as you want. You could spend a trillion human lifetimes, and it's just never going to happen because parallel lines, as we know, they never cross. And if they never cross, then we would say in this case that there is no solution. And the third one is the one that's always hardest to pry out of people just because it's so odd. Can you think of another thing that could happen if I graphed a line and then another line on the same piece of graph paper? No, if they're not straight, then they're not lines. Okay, so we are talking about straight lines here. These are linear equations. Another possibility is this. I give Seth an equation, and he gets y by itself, and he graphs it, and the line goes like this. And then I give an equation that doesn't look the same. Maybe it's in a different form, like point slope or standard or something like that. And then I give that equation to someone else and I say, graph that line. And when they graph their line, they realize that theirs looks like this. It is odd and it's difficult to conceive that this could happen, but it does happen. That sometimes within a system, your two lines are actually the exact same thing. They just don't look like it, right? One, it depends. And you've seen this before, like a point slope equation and a y equals mx plus b equation can be the exact same thing and look nothing like each other. So it is possible that you can graph two lines and they can actually sit right on top of each other. How many times do these lines, quote unquote, cross each other? Right. And so we say that a system like this has infinite solutions. Full disclosure, quite honestly, the vast majority of the systems that we work with are going to be from the first group. Lines that just cross. And that's what we're going to be spending the bulk of our time doing is finding that magic point. Where do the lines cross each other? So when we leave graphing today or tomorrow, it won't take long at all. This is a really easy little section. Then we'll get into the algebraic methods where we don't actually see the lines. Today, you're going to see two lines and you're going to, with your eyeballs, go, I see right where they cross. I can name that point. That's the solution. Whereas with the algebraic methods, bless you, we don't really graph. We just do things with X's and Y's and parentheses and moving things around. And that's why they're called the algebraic methods. So there's your kind of crash course on what a system is. It's two equations, two or more, but generally at this level, we're just going to do two lines, and we're going to see where they cross. Simple pimple, right? So the way I'm going to show you this is just by using Delta Math because your assignment's going to be in Delta Math. So I figured let's just look at it from there. And I had it do a mixed bag for you. So some of the problems that you see are going to look like this. And I'm just going to walk you right through how to do this. You're already familiar with the graphing interface because you've done this months ago in Delta Math, probably sometime in December, if I had to guess, where you just had to graph lines. And you know that the way Delta Math does graphing, it's pretty slick. I don't need a ruler. I just need to be able to clicky click some points, right? So what's nice about this system? Maybe if I showed you a different one, you might be more apt to answer that question. But what is nice about this as is? If I say let's go graph us some lines, what's nice? I don't have to do any math at all. These lines, these equations are both in slope-intercept form. They're both y equals mx plus b. So the first one, for example, I'm going to just move it down here a little bit, is y equals 3x minus 8. So where will I start that graph? Be more specific, please. I'm going to go down 8, and I'm going to click a dot like that. And what's his slope? Up 3?
Right one.
Right one. Thank you. And notice I don't have to click multiple points. I love the way Delta doesn't do everything perfect, but the graphing, they nailed it. They have graphing just on lockdown. It's perfect. So there's my slope intercept, slope of up 3, right 1, y-intercept of down 8. Now what I'm going to do is I'm going to graph the second line, and I'm going to see where they cross. I say you should find this to be a very simple assignment. So the next one is y equals negative 2x minus 3. Where will I start that graph? Down 3. Good job using your words there. So I'm going to go down 3 and click a dot. And what's the slope?
Down to
Down 2, right 1. Okay. And now I can see it doesn't probably take a math degree to see that these lines do in fact cross, and they cross at this point, we would agree right here. What is the name of that point? It's called the solution, right? But like, what are his coordinates? 1, -5. So we just solved a system by graphing it. So I'm going to go down into the box and I'm going to type in the answer 1, -5. And of course, notation matters. So I'm going to do open parenthesis, 1, comma, -5, close parenthesis, and then hit send. I don't think you're going to see a lot of weird stuff today. Today is really just to familiarize you with what you're doing. You're graphing two lines and seeing where they cross. Any thoughts on what might happen if I choose these level 2 problems? Let's take a look. What do you notice? I don't mind fractions.
The y is by itself.
Yes, one of the equations I have to do a little bit of math, very simple math, too. But the good news is that the top equation is already ready to go, right? But the bottom equation, no bueno, right? So how are we going to take this bottom equation and get it prepped? Heck yeah, let's move that x to the other side. So if I subtract away the x, what will it now say? Nice job. So I'm just moving these down again so that I can graph when I scroll. So my two equations now are here, and they're both ready to go. One was already ready. The other, we had to do some little itty bitty mathematics to get it ready. And so now I'm going to scroll down and help me graph, would you? How do you graph? Let's do the red one first. How do we graph that?
Oh.
What's his slope? Good. And you can go up one right to a whole bunch of times if you, not that you'd want to, but you could. It's going to all come out in the wash, right? And how about the purple line? Where do I start him at? Down 8. And then what's his slope?
Down, right.
Yeah, you could go down and right, you could go up and left, and again, you could go as far as you want. Like that's what I just did is go up 10 and left 10, and that's fine because it still gives the right slope of a down one, right one ratio. And then I just have to eyeball it. What's the name of that point where they cross?
8, 0.
Nice job. Perfect. -8, 0. So I'm just going to go down here, parenthesis, -8, comma, 0, close parenthesis. I want to stress again, notation matters, okay? These are points, and we express points with parentheses and a comma in the middle. And order, of course, matters. I had $1 for every time someone called me over and said, I swear I did this right, but then they have like their numbers backwards. Obviously, that's not going to work, right? So X comes first and Y comes second. And that's it. And they're not difficult at all. Like they'll maybe get a little bit harder tomorrow when I give you a separate assignment. But for now, I could keep doing new problem and you're going to see like they're just not difficult at all. How about this one? How would I get Y by itself on that second equation? That will not work for me. How about this? Feel free to give your input as to what I just did. Talk to me. How in the world did I get the Y across there? Why in the world is it suddenly positive? I did. I didn't show my work, but I just added the Y across to the other side. And then tell me this, why or how is the 2 on the other side now with a minus? What's this all about? I subtracted it. And I did this because if the Y is negative, then I want to move it. We've talked about this, I think, at decent length, that you should never move a Y unless you have a good reason to. But in this case, I saw a real clear path to my end. And I thought, well, heck, if I could just move the Y and then switch them with the 2, boom, I'm done, right? So yeah, this is what you'll be doing today after you complete this Y-top sheet. And the Y-top sheet we will go over. And the reason I'm doing it in this order is because some of you are going to take 2 minutes and blow through this Y-top sheet. Some of you are going to take a little longer. And I wanted to make sure that as you get done, you're not just sitting there staring at me, that you can go right in, flip open your Chromebooks and get cracking on this Delta Math. Okay. You should blow through this pretty quick. Any questions about that? There'll come a time tomorrow when I give you this assignment again, but on paper. And I'm going to make it a little bit more intensive where there's a little bit more work on the front end where you've got to, move some things around and maybe divide everything by 2, stuff like that. Where getting Y by itself will be a little tougher for you. But for today, easy breezy, warm up assignment. Okay. And I'm going to leave the recording going just because I'm going to add on to it when we go over the Y-top sheet. So This should have been about a 5-minute assignment. So if you're still working, it's okay. This isn't like a grade or anything. I'm just trying to get you to see the light. So if you're on your Delta, if you could please stop just for a couple minutes. This won't take me long, okay? So in question one, what I'm trying to get you to do is take the input, which in this case is the 4m, and put it in place of the x's, like where these arrows are pointing. So showing your work would be a really good move here. So where it used to say x squared, it's now going to say blank squared. And where it used to say minus 3 times x, it's now going to say minus 3 times blank. And then the plus 6 is just not going to change. So that's a constant. And in those blanks, I'm going to put the food, the input, which is this thing up here in the corner of the 4m. So I'm going to put 4m here and 4m here. And as you saw on Thursday, this is not a very exciting problem. It's just either you know it or you don't. When you square this first part, you get 16m squared. When you multiply the second part, you get minus 12m. And then that's it. That's actually the final answer. And does anyone remember why we can't go any further? Yeah, right. They're not like terms, huh? There's an m squared on one, there's a regular m on the other, and there's no m's on the other one. So none of the terms could be added or subtracted from each other. So that's it. Okay. Second problem is basically the exact same thing, but there's a little bit of extra work at the end because there will be two like terms, as you'll see. So the same idea applies. The idea is that the c minus 5 is the food. That's the input, and it's going to go right where this purple arrow is pointing right up here. And again, showing work is just what an intelligent person probably would or should do. So what it's going to look like is negative 2 times blank minus 11. And then into that blank is going to go the input. And the input could be anything. In this case, I just decided let's have it be c minus 5. I could have picked anything. Yeah. But now what we're going to do is we're going to math it out. And from this point, this has nothing to do with like anything odd. It's just distribution and combining of like terms. So when I do my distribution with these little green arrows, what am I going to get right there for those two answers? What's negative 2 times c? Nice. And then what's negative 2 times negative 5? Positive. So plus 10. And then you can see, unlike his predecessor in this problem, there are two terms at the end. I'm underlining them for you that can go together, right? So we always look for things that can go together. So in this case, like 10 minus 11 is negative 1. So we should, for a final answer, have negative 2c minus 1.
Those ones confuse me.
Question 3, the first question 3. What I'm going for here, and if you were here, you're totally probably familiar with what my goal is I want you to write an inequality. And so it's right here. The word is right here, write an inequality. And so what it's going to look like is basically, you know how businesses work. How much money you make minus how much money you spend gives you what's called a profit, right? And if your profit is positive, it's called a profit. If it's negative, it's called a loss. And so what I want though is to say, okay, how much money am I going to make? Well, I'm going to make $8.75 for every cake I sell. So that's 8.75 times X. But then I have to subtract. Subtraction is always going to be a thing because you have to, things don't just happen out of nowhere. To make a bunch of cakes, you have to buy a ton of ingredients, probably a bunch of pans and Lord knows what else. And so you spent $925. And what we want is for our profit to be at least, I'm underlining it up here in the corner, that means greater than or equal to $750. So what this inequality, it's like an equation. What it represents is I want the money that I make minus the money that I had to spend be at least 750 bucks profit. And that's the word problemy side of things. And now the rest of it is just low level simple algebra, right? And it does say in this problem to write and solve. So how would I solve this math problem that we've created? Add 925, right? Yeah. I mean, algebra never, ever, 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 ever will change. You'll use algebra always. Algebra someday to you isn't going to be a class. It's going to be just a thing. It's a tool that you carry around. It's a set of skills. And you know that to solve math problems like this, you have to get x by itself. And step one is to murder that 925. So we have to add 925 to both sides. And we're going to be left with 8.75 times x is greater than or equal to 1,675. And again, we're not in any kind of word problem right now. We're just mathing. What's the last thing to do to get x by itself? Divide by 8.75. And when you type that in, I had to use my calculator for this. It came out to x is greater than or equal to. It was like 100 and I'll write this down. My calculator said 191.42857 dot dot dot. Which should I round that up to 192 or round it down to 191? Don't answer this in a math way. Use your brain. What should I do? What's that? Round up. Listen, I understand that there's a 4 after the decimal point, and the math gods would say round down because it's not a 5 or above. But if I sell 191 cakes, did I clear my profit? No. If you think about it, somewhere in between the 191st and the 192nd cake, I achieve my goal of my profit that I want. So even though it says mathematically I should round down, my answer would be that they need to sell at least 192 cakes. Because again, if I round down, I don't quite make it. I probably come up a couple dollars short of my $750 goal. So you don't always follow the rules of rounding if it's a word problem. Think about what you're trying to accomplish. The next question 3 should be short and sweet. This one takes not very long at all. It's very quick. Marcus has decided to start riding an exercise bike. You've seen this problem before. It was a piano problem before. And the next time you see it, I'll change it again. Maybe someone jogging or something like that, or practicing the violin, who knows? But the idea is that how many minutes Marcus rides his bike, y, will be equal to how many minutes he rode it for on the first day, which is 30, plus how many minutes he adds every day, 2 times x, done. That's it. Now, if I asked a follow-up question like how many minutes does Marcus ride his bike on the 14th day, then you would do 30 plus 2 times 14. That's 30 plus 28, which is, oh, he rode his bike for 58 minutes on the 14th day, right? But all I'm asking you to do in this problem is just write me what we call a model or an equation, and that's it. Okay, question 4, which is actually question 5. You've seen this before as well. So how much oil is in the tank can be y. And again, it's going to be how much do I have minus how much am I losing? How much oil's in the tank? Well, 500. And how much am I losing? 1.5 gallons per x per minute. And again, that's it. And if someone had said, all right, how many gallons of oil are left in the tank after 25 minutes, then I could do 500 minus 1.5 times 25 minutes if I wanted to, but that was not part of this particular question. Simple. Do you guys remember the name of this? Question 5. This is going to be a really big thing going forward for us. What type of function is this? Anybody get it stuck in their head? If not, I can see this is something we're going to have to revisit quite frequently. Do you see how there's an x up in the exponent? It's called an exponential function, and I need you to know that. Okay. And you might even remember, if you have a super good memory on the y-top, when you graph something like this, exponential functions are always going to look kind of the same. The way this one goes, if you graph it, is it goes like this. And I tried to explain to you why on Thursday it does that. And that's because that exponent has amazing mathematical powers. When you start putting in big numbers for x, it grows crazy fast. And so that's what an exponential function will look like. How did you feel on that? Did you feel like you had some success? Here's what I would think. Here's what I would hope. When you saw those questions the first time last Tuesday or whatever that was, you probably were like, what the what? Hopefully today you saw them and you were a little less like that, maybe a little more inclined to get them right. When you see them again on paper, I trust you'll do even better, right? Do you have any questions? Okay, tomorrow you'll be doing a combination of working on your Delta math and then also a paper assignment that I will give you at that time. Got it? Okay, cool.
Did you go up to?
Sure. Like, is that good?
Yeah.
Okay.
Thank you.
Yep.